In this section, we're going to look at discrete random variables. With these, we can do calculations involving probability, but two things we're really going to focus on is expected value and standard deviation for these discrete random variables. So expected value and standard deviation. So random variables are where we can have these specific outcomes. And it might be associated with some sort of event like rolling a die or flipping a coin, or they can just tell us these possible outcomes. These outcomes are numerical, so they'll have some value to them. And then each outcome is going to have a probability attached to it. Either they tell us the probability, or we can calculate it using the rules that we've learned before. For some notation, what you'll see pop up in this section is using capital X to represent this possible variable, and even going to looking at probability using notation with probability of X, which is going to lead to like the probability of a certain outcome. So with this, I'll write out the notation as you'll see it come up as it will come up in the videos and in our book and things like that. It's good to be able to interpret the notation, but it isn't required for this course for you to write it out. But it's good to know where the numbers are coming from. So let's look at this example and see how probability ties in here. What we have here in this table, this is called a probability distribution. It's a probability distribution. It's a probability distribution table. What it combines is this random variable and the probabilities associated. So this first row is going to be our variable X, and what that'll represent is the number of cups sold at this cafe in a day. So what we could see from this table is that they could sell 30 cups in a day, 36, 42, 48, and 60. And just for the sake of this example, we're going to say those are the only possibilities. In the time that they recorded this data, no other value came through in terms of number of cups of coffee sold in a day. Then what we have is another row that are the probabilities associated with each of those values. So we have this 0.05, 0.2, so on and so forth. So reading these numbers together, what this would represent is that them selling 30 cups in a day has a 5% chance of occurring. Selling 36 cups in a day, 20% chance. 42 cups in a day, 25%. So you can see for each of these outcomes for the cafe, there's a probability for each of those outcomes associated with it. So if we wanted to answer questions involving probabilities, so what's the probability the cafe sold 36 cups of coffee? So for notation, what I would write here is what's the probability that our variable is 36? And just reading from our table, what we do is just grab the probability next to it, which was the 0.2. So that would mean there is a 20% chance the cafe sold 36 cups of coffee in a day. With this next one, what's the probability that they sold 36 or 48? And just like our rules before, that's going to bring through addition. Now, these will always be disjoint cases with these discrete random variables. There won't be overlap coming through. So with that, what we're doing is taking the probability of seeing 36 plus the probability of seeing 48. So 36 was the 0.2, 48 is the 0.15. So this will be a 0.35. So there is a 35% chance the cafe sold 36 or 48 cups of coffee. All right. Now this will be some wording that we haven't seen yet, and we'll want to get used to interpreting these for the next few sections when we deal with probability. So what's the probability that the cafe sold at least 48 cups of coffee? Now when you see at least, what that could translate to is more than or equal to. And in my notation for probability, that's exactly what I'm going to write. This is the same thing as looking for a variable being larger than or equal to 48. Whereas before we even solve that one, the next one's going with the wording of at most. So probability of at most 36 cups of coffee, and that's the equivalent of less than or equal to. So this will be written as the probability that our value for x is less than or equal to 36. So the wording here is common for students to flip it around because at least it sounds like you want to go to the left side. But the idea is like if I said, today I'm going to eat at least 5 cookies, what that would sound like is, okay, I'm going to start at 5 cookies and then I could eat even more from there and as many as I want above that. So saying at least something tells you the least value that'll come through and you want everything larger than. Whereas with at most, it's telling you the most value. So if I said, today I'm going to eat at most 5 cookies, then I'm saying I'm limiting myself to 5 and anything less than that is okay as well. So with this in our table, how we're going to calculate this probability of at least 48, it includes 48 and then we want everything to the right of it, so everything above. So what we'll do is it comes through as kind of an or scenario and that we're going to add these up. So probability of at least 48, it's like seeing 48 or 60. So we'll add those together. So there is a 50% chance. Again, with probability, then the rest is just kind of copying the wording from the question itself, that the cafe sold at least 48 cups of coffee. Now when we go to at most 36, it's giving us the largest value that we want to see, and then we want to see everything less than. So we're going to go to this left-hand side. It's like saying 30 or 36. So we could take 36 or 30 for a 0.25. So there is a 25% chance. Now this probability distribution table, what we should notice is what happens when we add up our probabilities. So with all of these probabilities coming through, we should make sure that this is actually our sample space, that we are seeing absolutely every possibility occur within this table. And to do that, what you can do is add them up. And what should happen is they should always add up to exactly 1, or the idea of 100%, to represent our total sample space so nothing's being left out and there isn't too much included in the table. So part E here is going to get at expected value. So there are formulas that we'll see on the next page here for expected value and standard deviation, but I'm just going to break it down a bit for you so you know where these formulas come from. It makes it a little easier to apply it to. So expected value, this is the same idea as average or mean. So what I want to do is a quick little comparison of how we would usually calculate mean. So if I told you this cafe, they could sell these certain number of cups of coffee in a day, and I wanted you to average them, well, how we would usually do that is add them up and divide by how many there are. So we would take that 30 plus 36 plus 42 plus 48 plus 60 and then divide by 5. Now I'm going to leave a little space here because I just want to show you some steps here that are kind of, it's extra work, but it'll tie together nicely with our formula. But the idea is that if you calculate that, and I'll put it at the end here, you'd get this 43.2. Now, just to rearrange this calculation a little bit, and some things that are at work when we're taking an average, I could rearrange this and it would be the same exact calculation if I kind of distributed our fraction of 1/5 to each piece that we're seeing there. So if I wrote it this way, it's exactly the same calculation. And then I'm just going to take it one step further and just change that to a decimal. So what we're seeing happen here, and so what an average does, is taking each of those outcomes that we had, and evenly distributing it, meaning each piece in this case is worth 20% of the sample space. So we see an outcome of 30, and that's happening 20% of the time. 36, 20% of the time. 42, 20%. So it's giving this even distribution for taking the average. So, and that works with all of the means we've done so far. It's always been this even distribution. But what's happening in this section is now we don't have an even distribution anymore because of those probabilities. What these probabilities tell me is how to weight the values, meaning we see an outcome of 30, but that only happens 5% of the time, which is not very often. So if we're taking average and how we usually did it and having 30 be representing 20% of the data, it's not very, we shouldn't have an even distribution here. It's giving too much weight to that 30. And then like the outcome of 60, which has a 35% chance, we want to give some weight to that. That has the highest probability of occurring. So in terms of average and expected value, in terms of what we expect, we want to give weight to the things we expect more and weight to the things we expect less, so that we're distributing these probabilities across our values. So this idea of expected value, you might have heard the term weighted mean before, and that's what we're doing, or weighted average. It's more common. This is what's used to calculate your grades in the class, where you have a certain percentage for exams and certain percentage for homework. This is how it's calculated, so that if you get like, usually a lower weight grade is participation. So if you get 100% in participation, it's great, but it doesn't have as much of a weight as like if you got 100% on your final exam, which would have a stronger weight in your grade. So what we do is we're going to use the structure that we see down here, where we took each of the outcomes and multiplied by 20% when it was an even weight. But what we need to do is adjust it to the weights that we actually have from our table. So what we do is we take each outcome multiplied by its probability. So in our case, that would be a 0.05, a 0.2, a 0.25, 0.15, and 0.35. And if we do that, we'll get a 47.4 out. So what we could do is even compare in terms of what we had for our weighted mean versus what we would get usually just by taking the direct mean. We have something larger, and that's coming from the idea that these higher probabilities are occurring in these upper values. So where that original mean, that 43.2 kind of lands here, with that high weight of 60, it got pulled to the right, as it should be. In terms of expected value, we want the mean to follow these probabilities. So I'm just going to go ahead and cross out. We don't want to do that anymore because it's not accurate for this scenario. Since we have the probabilities, this is the correct expected value. So in terms of a sentence, we could say the cafe can expect to sell about 47 cups of coffee in a day. All right, so that's expected value. It's going to come down to taking each of the x values times their probabilities and add it with the next one and the next one and so on and so forth. So for a formula, that's what we're seeing at the top here. I'm just going to draw a little line here to separate our next step that we'll do. Expected value, same thing as, or at least similar to weighted average in this case. So since we have our total sample space, the notation that we use is your population mean. So you can use that symbol, or you can use this E of X, which is just saying the expected value of our random variable. And then in terms of a formula, if you remember from when we learned standard deviation, that just means add. So that's why across our data table, we're adding each of those pieces. And then it's just the X value times its probability. So what we do is we add up the outcomes times their probabilities. and that's how we'll get expected value. The next video will have some practice with these, so you'll get to see this applied a little bit more. In this video, we're just going to get the formulas going. Now, if you see these formulas for variance and standard deviation, it might just look like a bunch of gibberish, and in fact, I'm missing a symbol here. Sorry about that. There should be... Oh, there's a lot missing from that. I'm missing that symbol, and I'm missing a square root. Sorry about that, guys. Square root and summation symbol should all be there. But again, oh, it is there. Sorry, this is a mess, but we're so far into the video, I'm just gonna squeeze the addition symbol. But what I'm gonna do is break it down in words for you, so even if it's not easy to read, I'll fix this on your, on the printout notes. It'll just be wrong on the video notes. With this, I'll break it down in words and kind of give you a step-by-step process for how to go through this, kind of like we did with standard deviation, and that sometimes it's easier to arrange it in table form rather than plugging into the formula all at once. Now, when we learned mean and standard deviation before, we had GeoGebra for when we have a lot of data to plug in and find standard deviation for us. For these, we have to do this by hand. I mean, we'll be able to plug it all into a calculator, but I'll give you a breakdown that kind of helps with arranging that. So let's start with what standard deviation is. As a reminder, it's that average distance from the mean. So when we found standard deviation before, what we ended up doing was looking for the deviations to get the idea of distance from the mean, but we had to square them to get rid of any negative values. So that'll be our first step here. First thing we're going to do is let's get those squared deviations, but for this type of data. So squared deviations, where you take the x value minus the mean squared. In this case, our mean is a population mean since we have our whole sample space. So what I'm going to do is kind of make a table here for our squared deviations. So squared deviations, I'm going to take my x value, and for our first x value, we can use that 30 minus the mean squared. So there's one of them, and then I'll go to the next data value, 36 minus the mean squared, and the next, and we'll basically go through and just plug in each value minus that mean squared. All right, so there's all our squared deviations. Now, when we took standard deviation before, what we wanted to do was add them up and average them. And when we did, we added them up and then divided by the sample size minus 1, if you remember that. Here is kind of the equivalent to what happened when we found the mean this original way, where that's not going to work. This adding up and dividing by how many there are isn't going to give us our correct value because we have the weights. So even with how the weights behaved with mean is the same idea that how 60 deviates from the mean, it's occurring more often. It has a higher percent chance of occurring than how 30 deviates from the mean. So similar to what we did up here, instead of adding them up and dividing by how many there are, we're going to multiply each value by its probability to scale it accordingly. So, I'm sorry, I just noticed that should be a 35. All right, so what we're going to do is take each of those and multiply by its probability. So that'll be our second step. So we find our squared deviations, and then we're going to multiply each by its probability. So I'm going to go times 0.05 times 0.2 times 0.25 times 0.15 times 0.35. So with that, that's getting at the idea of this average distance from the mean. However, we're still at that squared stage, but what we just did is we're en route to finding the variance right now. Remember, so this symbol means to add. Here's our squared deviations, and here's our probability, and that's just what we did. Here's our square deviations. Here's our probability. I don't really need to write that again. It is what it is. And then what we want to do to find variance is we want to add up those values. So what we're going to do is combine them. We're going to add them all together. And when we do this, that'll find variance. Now this is the spot where we want to go to a calculator. So I have my calculator open here, and I'm just going to show you how to plug it in because that's often the tricky part of this. And with this, we'll just write this long line of addition. So we'll have our 30 minus 47.4 squared, and then times its probability, and then add it with the next piece. And I'm going to keep typing here. Sorry, I know this will make for a long video, but if you're comfortable with typing in, you can go ahead and skip ahead to the punchline of this. But just in case you're not, I want to show you step by step. You can also, as you're typing here, just using the keyboard, for the squared, what you'll notice is I'm typing in, I use this Shift 6, it's kind of the caret top button, sends me to the exponent, but there's also this button here for squared, and you could just type that one there, and then times probability. And almost there. But this would be good if you even want to pause the video and try this for yourself, because it's often this typing in where the errors occur. Type it in and make sure you can get the same answer out, but we should be getting this 104.04 here. And what's nice with, I'm in the Desmos calculator, but it's very similar with the GeoGebra one. You can kind of scroll around and edit if you made any mistakes or left out. Often leaving out the exponent of 2 is a common mistake here, or just switching multiplication and addition in spots. But you can go in and edit if you need to. So 104.04, that is our variance. So that calculation right there is our formula up here. What we're doing is we're adding up the square deviations times their probabilities. Now to get to standard deviation, you'll notice there's our square deviations times their probabilities. I left out that addition symbol, sorry about that. But all we're missing is the square root over all of it. So just like before with variance and standard deviation, with variance, our units are squared. So to get back to our correct units, we need to take the square root. So my next step, my step's up here. So we added to get variance. And then our last step is going to be to square root that value once we have that sum. So for standard deviation, we'll be taking the square root of this 104.04. Now in this case, it came out to a nice round number. In general, try round to 4 decimal places, or even better, with working with these calculators, you can copy and paste things. So just in case this was a super long decimal, just to keep things as accurate as possible, what you could do is use the answer function within the online calculator. So if I type my square root and I want this previous answer, if it was really complicated and I didn't want to type it all in, there's this button right here for answer, and it will just copy and paste whatever you had to an exact value. So just for those complicated ones, try using that, so that with too much rounding, especially rounding with squares and square roots, you want to avoid rounding as much as possible. So our final answer is a 10.2. So 10.2, and how we interpret this is just like before. I would say the expected value. So the cafe expects to sell about 47 cups of coffee each day. And on average, this differs by about 10 cups of coffee. So expected value gives us exactly what we expect, and then standard deviation tells us how we expect that to change, in this case, about 10. Now, a common question that comes up here is like 47, that wasn't an outcome on our table, but this is the idea of long-run behavior. If we've repeated this process for days and days and days, overall how it would average out is we'd expect that 47. I'll talk about that more with our next examples as well. But that's mean and standard deviation using discrete random variables.